Welcome to lecture number 29. To summarize the previous session, we completed the last part of the Fourier representation, that is Fourier transform in the previous class. And as you know, Fourier transform is applied for a non-periodic continuous time signal. So we could also observe how to find the time domain signal for the given ft coefficients, which we call it as inverse Fourier transform. And in this session, we are understanding, or rather I can say, we are comparing the various Fourier representations and we try to understand the concept behind it. Okay, so let me share my screen. Yes, in lecture 29, we are concluding chapter number 3, that is frequency domain representation of LTI system. Today's topics that we are looking into are Fourier representation comparison. That is, we have come across 4 Fourier representations: DTFS, FS, DTFT, and FT. We will compare all those things and a revisit conceptually. So here's a table I have made in order to illustrate you the importance of the Fourier representation. The very first one is, you can see here across the column I'm having periodic. So here I'll be listing out the periodic signal, and across the first row I'm having continuous time, and in the second column I am having non-periodic, and in the second row I'm having discrete. So whatever comes over here, it is, I can change the ink. So it is periodic and CT signal. Continuous time signal, periodic signal. So if it is periodic and continuous time signal, I should apply Fourier series. And periodic signal, the independent variable is uh, t for continuous time. So let me write it here. This is an independent variable t. Okay. And similarly for discrete time, periodic signal, we have discrete time Fourier series. So this is applied for periodic DTS. And what is the independent variable here? It is n. So n is an independent variable. So these things you should keep in your mind. So then that is what is written here, n here, t here, and I should have written n. And what about frequency component? So if it's a frequency component, you know, frequency component will be discrete. This is the Fourier domain. In Fourier domain, how the signal looks? Fourier domain for periodic signals, how it looks? It looks discrete. Your Fourier domain signal is of discrete time. That's the meaning. Please understand it. It's very important. So you have a signal called x of t or x of n, which are periodic. So once you apply, periodic means you will be either applying FS or DTFS. I can say series, and whatever signal you comes out, that is x of k. This x of k, the frequency component is represented, the variable is k. So this will be discrete kind. This will be a discrete kind. That's the meaning. That's the meaning of this. And now to analyze the one more column, that is non-periodic signal. So here the period is, you should also remember this. The period is omega naught 2 pi by d, and here omega naught, capital omega naught 2 pi by n. In both the cases, what you're supposed to do is you should write it as omega naught because it's a period. Period is defined, right? The time domain signals period is omega naught. The time domain signals period is capital omega naught. That's how you should write it. And in non-periodic signal, you will not be having a period. So omega naught and capital omega naught does not come into account at all. So one second, I'll just make some modifications. This is small omega naught, this is capital omega naught. Okay, so this omega naught is used for continuous time angular frequency representation, and this capital omega naught is used for um, angular frequency representation of discrete time domain. Okay, so for non-periodic signal, t is an independent variable for continuous time, and for discrete time, n is an independent variable, that we know. Non-periodic and continuous. So hence Fourier transform, non-periodic, non-periodic and CTS. Okay. Similarly, here you can say that x of j omega, you don't have any period here, but it's ranging from minus infinity to infinity plus infinity. I'll come to it later again. So for non-periodic and discrete time, your signal is discrete time Fourier transform. So this is applied for non-periodic and DTS. The independent variable is n. So independent variable is n. So here you can check what about the Fourier domain. The Fourier domain signal looks like continuous. Okay, so here Fourier domain was looking like, I just check it out. Fourier domain was looking like the discrete, but here it is continuous. Okay, so that's a very important fundamental that you should remember. Whenever you perform transform, Fourier transform or DT, what I can say, discrete time Fourier transform, your frequency components are huge in number. Whereas if you check Fourier series or DTFS, the Fourier domain signal, the frequency components are countable. Discrete means it can be countable. Whereas in continuous means it is uncountable. So you have n number of frequency components. That's the meaning. Okay, so this is frequency domain. I'm talking about frequency domain. In frequency domain, the independent variable is k here if it is periodic in time domain. And here it is either omega, small omega or capital omega depending on whether it is continuous or discrete. Small omega for continuous, capital omega for DTS. And this is continuous in frequency domain. So this is the column wise answer. And now I'll go row wise. You just hear whenever we apply Fourier series and Fourier transform, it is applied for continuous time. So when you apply a continuous time signal, time domain signal, and you apply either Fourier series or Fourier transform based on periodic or non-periodic nature, whatever outcome you get at the frequency domain, so that will be of the nature non-periodic. Your frequency domain signal will be non-periodic here, non-periodic, and its independent variable is k if it is of fs, it is of omega, it is of ft. This is fs, this is ft. Okay, so for discrete time Fourier transform and discrete time Fourier series, for discrete time in general, for time domain signal which is discrete, if you convert it to Fourier domain either by DTFS or DTFT, the outcome in the frequency domain is a periodic frequency components whose independent variable is k for DTFS and capital omega for DTFT. This you should remember. And I can frame n number of one mark question out of this, n number of objective oriented or MCQs out of this table. I can go on asking like, what if the continuous time signal is applied at the time domain signal, and in the frequency domain dash kind of the signal appears. So if ft is applied, or I might not represent fs or ft, you should write it as it is a non-periodic nature frequency component. And periodic nature of frequency component can be bought or can be got when you apply discrete time signal at the time domain. So these such analysis either like this or like this. If I apply periodic signal at the time domain signal, if time domain signal, this is time domain signal, if it is periodic in nature, so what about the frequency domain? In frequency domain it is discrete. Okay, so if it is non-periodic, it is it is continuous. So I'll bundle it up just here. And one more important thing is DTFT, though it is continuous and it is periodic with a period 2 pi. So varying from minus pi to plus pi, minus pi to plus pi, that you should remember. So I'll put in front of you the summary kind of listing here, just here. So I have a Fourier representation. This is Fourier representation. Okay. So if I supply the periodic signal, whether it is continuous or discrete, later on we will vary. So the outcome, this is time domain signal. This is frequency domain signal. Okay. One by one, I'm fetching and I'm just explaining you. So time domain signal is periodic. I am for using Fourier representation for representing a periodic signal. So at the output, what do I get? I get discrete time. Period frequency domain signal will be in the form of discrete time. So in both the case, the independent variable is k. Because in periodic, if you apply DTS or CTS, for DTS periodic signal, you apply DTFS, and here it is FS. So it is series. So it is always a series when you apply periodic signal. And what is the outcome? The outcome is discrete time, or sorry, signal, discrete signal in frequency domain, and whose independent variable is k. I'll take in this way. See, periodic means a signal repeats after certain time interval. If this is t, after every t, this is 2t, this is 3t, the same signal repeats. Whatever signal I got it here, same signal comes over here, same signal comes over here, and goes on repeating. So if it is repeating, analysis of the same repeated signal is of useless. So I don't consider it. My whole concentration will be on only one period. And in one period, the signal might be like this or like this or like this. So this signal, these two signals, this signal and this signal, if I want to reproduce by the superposition of complex sinusoids, I should decide how many frequency components I need. So to represent this signal, it's comparatively a smaller kind of signal, a section of signal, because thereafter it is repetition. So I need comparatively less number of frequency components in order to produce this. So hence it is discrete. Less number of frequency components, or discrete means it can be countable. Countable number of frequency components are sufficient for me to reproduce the periodic signal at the time domain. Or the periodic signal can be represented using less number of frequency components, okay, compared to non-periodic. That's the meaning. So bit hard to understand this concept, and it's you will not get a clear idea if you just read the textbook. That's why I'm stressing upon it. Now same thing, if I apply non-periodic signal, if I apply non-periodic signal non-periodic signal, again I have DTS and CTS. So if it is non-periodic and DTS, I'll be applying DT, FT, and this is what this is just FT. And if I apply a Fourier representation, so actually it is transform based on what kind of the signal I'm applying, whether it is discrete or continuous, but it is non-periodic signal. So if it is non-periodic signal in the time domain, in the frequency domain, how it will be? I'll just show you the table. If it is non-periodic signal in frequency domain, how it should be? It will be continuous. So it will be continuous. It will be continuous signal. So independent variable are omega and capital omega. So this omega is used for whenever I apply FT or CTS. So this capital omega is used for representation of DTS or DTFT. So DTFT, DTS signal, non-periodic signal is applied. You'll be applying DTFT, you get continuous signal, and in that case, the independent variable is capital omega. So that's what is the meaning. And here one thing you should understand is non-periodic signal means it will never repeat. The signal might be like this. Oh, sorry, it will not go backside. So like this, it will not repeat at all. It will not repeat at all. Okay, so when it is not repeating, producing this kind of the signal, representing this kind of the signal needs lot of frequency components. Lot of frequency component. I don't have only single section to be represented. I have whole lot of the signal to represent. Okay, and to extract the frequency out of it, you can see lot of frequency components. Here, if I check the time period is different, means frequency is different. Here the frequency is different. Here the frequency is different. So I can say to represent this kind of non-periodic signal, I need lot of frequency components. So if I just put that frequency components and its amplitude in this fashion, like amplitude and frequency, it will be so huge that and if you just draw a curve, it looks like a continuous. That's why I'll say that it will produce a continuous signal of frequency components at the frequency domain, Fourier domain. So whenever you apply non-periodic signal, it's guaranteed that at the output you will be having lot of frequency components in the Fourier domain. And we don't call it as lot of, rather we call it as continuum of frequency. We call it as continuum of frequency component, or series of frequency component, or continuous frequency components. That's the meaning. And one just highlighting point here is, for the discrete time Fourier transform, the period is this one. The period is minus pi to plus pi. Remember this, because after that it goes on repeating. That we will come to the analysis of this when we go row wise. Now we have went on column wise. This analysis is by analyzing that table column wise. Column wise when I analyzed, periodic I applied, I got discrete at the output. Non-periodic I applied, I got continuous at the output. That's how I analyzed. Now I go row wise analysis. Row wise. So row wise, I put in front of you the table. Row wise, first I'm feeding the continuous time signal, what I get at the output. Next I feed discrete time to the Fourier representation, what I get at the output. That we will check. So first thing, I apply Fourier representation. This is time domain signal. This is a frequency domain signal. So here's the input, this is output. Now at the input, I am having continuous time signal. If I am having a continuous time signal at the input, it can be either periodic or non-periodic, anything it might be. But it is a continuous time signal. If it is periodic, we apply Fs. If it is non-periodic, we apply Ft. So that's why I'm just writing Fourier representation. Series or transform according to the periodic or non-periodicity. So if I apply just continuous time signal without worrying whether it is periodic or non-periodic, what is guaranteed at the output of the frequency Fourier representation is you will get a non-periodic signal. Non-periodic signal. So independent variable is k and omega. So k for when you apply Fs, that is periodic, and omega for when you apply Ft when it is non-periodic. That you should remember. So if you apply continuous time signal, frequency domain signal looks like non-periodic signal. Again, I come to the conceptual analysis. Continuous time signal is somewhat like this, like this, like this, like this, right? That is periodic or non-periodic. Think that the same thing repeats later, or it is just a non-periodic. So here I'll be having a frequency components which are not rightly arranged. Okay, so it can have even the fractional part also. This fundamental will be cleared when I explain the discrete time. Until then, you please wait. Okay, so I am telling, so the fractional part of the periods are also allowed here. Okay, so that's why you get a non-periodic signal frequency components at the Fourier domain, and k is an independent variable if it is a periodic continuous time signal, and if it is non-periodic continuous time signal, omega is applied as an independent variable. Now the same Fourier representation I apply in order to produce the output when my input is discrete time signal. So discrete time signal, again I have periodic and non-periodic. So periodic means I apply dt Fs, non-periodic means dt Ft. So again I get, just here, I get a periodic nature. I get a periodic nature signal. So periodic nature signal, again the k and capital omega. K and capital omega. So k is for dt Fs, so when it is periodic input, and this is dt Ft when it is non-periodic input. Non-periodic input. So here the things will be much more clear for you. So when I apply DTFT. DTFS, it is easily it can be understandable because it is discrete time Fourier series and the output is periodic with respect to k. Whereas for non-periodic DTS, still I get a periodic nature frequency output. Why is that so? That is what is the thinking or that we need to do. See, I'll take one example. Think that if omega is 3.5 pi, if it is 3.5 pi, so I can represent it as 2 pi plus 1.5 pi. And you know that when we apply it for e raised to, because it is normally in the range e raised to j, it in the form e raised to j omega, e raised to j omega, right? In that form, if I apply e raised to j omega, if I write it 2 pi plus 1.5 pi, I can write it as e raised to j omega 2 pi into e raised to j omega 1.5 pi. So what is e raised to j omega j 2 pi? It is cos 2 pi plus j sin 2 pi. You know that sin 2 pi is 0, so imaginary part is vanished. So cos 2 pi is 1, so it will come to be 1. So you will be left with only e raised to j omega 1.5 pi. It's as good as writing 3.5 means it is as good as writing 1.5. Similarly, you give me any signal. You might take 5.7 pi. I can as well write it as 2 pi plus 1.7 pi. I can show that e raised to j2 pi into e raised to j2 pi is 1, and whatever is left is 1.7 pi. You take any number, it always falls in the range of 0 to 2 pi. And when it is periodic, by symmetric property of periodic nature, so I can as well write it as minus pi to plus pi. Both mean same, right? So minus pi to plus pi, the period is 2 pi, or else you can even consider it as 0 to 2 pi. Hence the DTFS omega is the non-periodic nature at the output. But same thing is not true here in FT. Same thing cannot be true because at 2 pi, at every 2 pi, it is a discrete domain, so hence you can do it, but here it is not possible. Hence it is non-periodic nature when you apply a continuous time signal non-periodic nature. So this is a row wise analysis and a column wise analysis. Once again, I take you to the table. So periodic and continuous, it is Fourier series. The equation goes like this. Remember, summation x of k means in Fourier domain, the signal is discrete. This is discrete signal. When it is discrete signal, the operation that should be applied to it is summation. X of k is a frequency component. Look at this. A frequency component is discrete type. So if it is discrete type, the mathematical operation to be performed is summation. Remember one thing. For discrete time, use summation. For discrete time, use summation. For continuous time, use integral. Remember this. X of k is discrete, so I'm using summation. Now look at the x of t time domain. X of t is a continuous time. So continuous time, integration should be applied. Remember. And it is a periodic nature. It is of periodic nature, so 1 by t, 0 to t. 1 by t, 0 to t. So that is how you should remember. Discrete time or continuous time, that you should make decision. If it is discrete times, apply summation. If it is continuous time, supply integration operation. And if it is periodic in nature, what is periodic here? Your time domain signal is periodic, so this is time domain, so I take 1 over t. Okay, and for periodic signals, x of t has a period from omega naught is equal to 2 pi by t. X of t has a period. Okay, remember this, not x of k. Fine. So now coming to discrete time Fourier series, you can see x of k is again still discrete, so it is applied with summation. Now coming to x of n. X of n is a discrete time, so it is a discrete time x of n. Hence the operation performed is summation. And you know that it is a periodic. X of n is a periodic nature. See, we are column wise. This is periodic in nature. So when it is periodic in nature, 1 over n from summation ranging from 0 to n minus 1, because x of n is periodic. Omega naught is equal to 2 pi by n. X of n is periodic. That's why we wrote it like this. Okay, so remember. Fine. Next, coming to non-periodic signal. So non-periodic signal, the frequency component is continuous. So hence I'm applying x of j omega is a frequency component. So for this I'm applying integration because it is continuous. It is continuous. Fine. But this is continuous. And then here the input time domain signal x of t. This x of t is a continuous time signal. So when it is continuous time signal, I should supply an integration operation. So integration operation is performed. Okay, so these things. And coming to discrete time Fourier transform. So integration is applied for the frequency component. Why? Because the frequency component is continuous. X of e j raised to j omega is continuous. And discrete time domain signal, hence summation is used. X of n summation is used. Fine. So these things you should remember carefully, and you should proceed with uh, understanding of this equation and writing this. You should practice writing all this equation. I just told you, or I'll just gave you a hint like how to recap or to remember these equations. Fourier series, for example, you want to remember Fourier series equation. How to remember it? Fourier series is applied for continuous time signal, right? Fs, just Fs, continuous time signal. So hence integration x of t you should write, or else you should start writing with x of t. And Fourier series will result in, Fourier series is a periodic. So periodic signal when it is applied at time domain, at the output it is guaranteed that you will get a discrete time. So hence summation x of k. So this particular continuous time signal at time domain can be represented with discrete time frequency components. So hence summation x of k. So this remains same. Here this omega naught, here this capital omega naught. So when representing continuous, I mean time domain signal, it is plus here, it is plus here, it is plus here, it is plus here. Minus appears only when you're representing frequency component. X of k negative here, x frequency component j omega negative here, e raised to j omega negative here, like that. Fine. And then x of t is a continuous time signal. So apply integration x of t, and you are applying series for periodic nature. So 0 to t, 1 over t. So this is how you can construct the equations of any Fourier representation. Why we should give so much of importance to Fourier representation? That is what we need to understand. So I'll take one out of the box example to explain you. Okay. So you know that when the prism was bombarded with white light or sunlight, we could see the spectrum, 7 colors. Okay. With fine. So this gave a revolution in light industry, or we could do lot many things here. Red was having highest wavelength, blue or bluish lights, violet was having lowest wavelength. This is a wavelength, lowest wavelength, highest wavelength. But when it comes to frequency, more wavelength means less frequency. This is less frequency. Lowest wavelength means high frequency. Lowest wavelength means high frequency. Highest wavelength means less frequency. So red was with less frequency, bluish lights were with high frequency. And because of these things, we could, do wonders in science field. And the same thing is possible even in signals and systems. See, what I'm doing is with this Fourier representation, the signal that I'm feeding will give me the frequency components. Like I can separate out high frequency component, low frequency component. I can separate it out. So what is the advantage of separating high frequency component and low frequency component? That might be your next doubt in your mind. I'll take a beautiful example. Image. Nowadays, we all are very much fond of taking pics, right? So image, when it is captured, When it is captured, there will be a lot of information hidden in it. Okay, so image has a smallest element called pixel. Okay, so these pixels, you know, these pixels are arranged in this fashion, and if you can check, the nearest pixels will be of almost same color, same kind. Whenever you have edge, think that there is an edge. The very next pixel will largely differ from the earlier pixel. So whenever there is a edge, there is a difference in the pixel color, or else the pixel looks same itself. For example, look at the screen itself. Here, if you check, I can make it in lot of pixels. Do you find any changes in the pixel? This is also white, this is also white, this is also white, this is also, yeah, everything is white. Now I want you people to consider this region, and I just cut it in terms of pixels, picture elements. Okay, this is same, this is same, this is same. But when it comes to edge, you can see here, this is not same as this. There is huge change, and this huge change we call it as high frequency component. Whenever there is a leap change between the neighboring pixels, we call it as high frequency. When there is no change, we call it as low frequency. There is no change at all. Now, what we get from this? So, what happens is, if I take out the low frequency components, if I take out the low frequency components from the image, then the output is, see, if I take the low frequency component, I'm scratching it out means I'm taking out. You are left with only high frequency components. It means in your image, only edges will be highlighted. Only edges will be highlighted. Rest of the things will be, you know, black color or blurred, or it will not be given importance at all. Only wherever edges are there, only that will be located. Okay, so because of this edge detection only, we can just scan the number board of a car, and we can detect what is that number. Machine can read its number, because that number will be filtered, edges will be filtered, or edges will be marked. We can read it as A for A, we can read it for 2 for 2, right? So the machine can do it. This is one of the application of edge detection. So I just took out the low frequency component. I am left with only high frequency component. Now my filtering process is easy. I can do such operations. Now what if I do the reverse thing? I take out the high frequency component out. Now I retain the low frequency. Then what happens is edges are not visible. So it looks blurrish. Now what is the use of this blurrish video or image? You might be feeling. But But in terms of memory, if I take out the high frequency component, this will be taking very much less memory. So that's why when you are watching YouTube lecture, if you keep it for 144p resolution standard, the handwriting looks blurred, because I have taken out the high frequency component. Still you are able to watch the video even in low bandwidth at your home. If your bandwidth is very less, it's better, like something is better than nothing, right? So at least blur video you can view. That's the reason, because initially low frequency components are transmitted through the transmission medium. So you'll be viewing blur videos. If your bandwidth is high, then we pump up high frequency components, that edges becomes clearer and clearer. So what happens if I remove the high frequency components is, I can store the images in very less space, very less space. Just remember, one image that you take in your camera, in your mobile phone, you take one image, and that image will consume at least 4 to 5 MB data, right? Everyone has a smartphone, I guess. Each image, one photo that you click, it will consume 4 MB of data, right? And you know that if you make a video in your cell phone, a normal thing is 30 frame per second. Hope you have referred this in your camera settings. 30 frame per second means, frame means pic. 30 pics it will take per second. It's as good as, if you're so fast in taking a photograph, if you take a photograph 30 times in a second, it's as good as you're making a video. Okay, you have to flap on your camera button 30 times per second, means 30 pics per second. It's as good as you're making a video. That's the meaning. Video is nothing but an image, remember. So for 1 second video, for 1 second video, 30 pics you are taking, each of 5 MB. So 30 5s are 3 5s are 150 MB for 1 second video, for just 1 second video. Okay, for you know one full movie, if it is 2 hours movie, if it is 2 hours movie, 2 hours means 2 into 60 minutes into 60 seconds. Am I right? I think it is correct. So if I multiply, it will be so huge. It will be in terms of GBs, not GBs, in terms of TBs, right? It will be so huge. But you can see that in your mobile phone or in your computer, you're storing a single movie, whole of the movie, in just 700 MB of data. How come it is possible? Because it is highly compressed. How it is highly compressed? It's because in most of the case, part of the high frequency components is removed, and in other cases, redundancies are removed. Redundancy, you will understand it later. You might have learned in your digital electronics about redundancies, repeating things. For extracting prime implicants, you will be removing redundancies, right? So like that, yeah, the same looking pixels we will be removing. Okay, so that's called redundancy. By removing redundancies and by removing high frequency components, by retaining only low frequency components, we can compress the image in a greater extent. So that's the reason why this Fourier representation plays a very important role, because I can separate the frequency components. So this is the importance and advantage and application of this chapter or Fourier representation. So with this, we are concluding today's lecture. Thank you.